history of diffraction and then introducing you to some of the key aspects of the theory of diffraction. Today I'll talk about single crystal diffraction, not because you're all going to use single crystal diffraction, but there are a lot of things there that are immediately transferable to powder diffraction, so I won't have to cover them again. But also, as you know, to get a paper published on a new compound, you'll have to have a crystal structure if you want to go into a reputable journal. Most of the papers that you'll be referencing and reading will have crystal structures in. So understanding what is being said about the crystal structure in that paper is important. So what I'll try to do today is tell you a little bit about that, how you can interpret some of the things, what they mean, and how you can calculate certain things like bond angles, bond lengths. So, and all these things are immediately transferable to powder diffraction. So, single crystal diffraction. The first step, if you're going to do single crystal diffraction, is to grow a crystal. How big is that crystal? Well, it depends on the diffractometer, and it depends how hard you have to work. So typically, around about 0.2 millimeters in each dimension. So a typical crystal would be, a perfect crystal would be something like 0.2 by 0.2 by 0.2 millimeters. But we rarely get a perfect crystal. So typically for an organic structure that is monoclinic, one of these would be long, you might have needles. That's okay, so long as you are roughly within these sort of dimensions. So we're not going to talk about crystal growth. How you grow crystals from solution is relatively straightforward. From the solid state, it's much more difficult, but it's well worth it. I can't emphasize enough to you how much more preferable it is, if you want to do structural analysis, to have a single crystal, even a small one of that size. Getting one of that size for some systems is impossible, and for those you must use powder diffraction, you have no other choice. But otherwise, if you can, you should try and grow a single crystal if you have access to a single crystal diffractometer. 0.2 to 0.4 millimeters in each dimension is ideal. What do? We normally have to mount that crystal on a goniometer head. So we stick a fibre, we mount it on a fibre, and then that's mounted on this goniometer head, and you can adjust. You can see there are little angles for moving, little screws here for moving the crystal up and down, side to side. So you can. So that allows you to center the crystal in the X-ray beam. For modern, in modern diffractometers, because we tend to work at low temperature, so typically at liquid nitrogen temperature. So a typical measurement will be from 80 to 100 K these days. And then you can use something like silicone oil. You can have your crystals dispersed in silicone oil, mounted on the end of a fibre, and then you freeze the silicone oil in the flow of nitrogen. So this is a nice method. Then you don't have to use glue like you had to use in the past. So we talked about von Laue's original experiment. Several different diffraction methods have evolved, including Laue's original method. So things like the precession method, the Weissenberg method, and then 3- and 4-circle diffractometry. Okay, I'm going to concentrate on 4-circle diffractometers because that's what we use, but there are plenty of very good 3-circle diffractometers, so have only 3 angles to play with. So you mount your crystal in the centre of 4 circles. What does that mean? Here's the crystal, and you have circles. Here's a typical, this is quite an old style diffractometer, but you have this crystal mounted in this sort of frame where you can rotate the crystal with respect to the X-ray beam and with respect to the detector arm. So we usually call these phi, chi, omega, and 2 theta. 2 theta is analogous to what we see in powder diffraction, so this is the same stepping of the detector. Chi, you can see, is this angle here. Phi is this rotation around the centre here. Omega allows us to rotate in this direction. So in fact, omega and 2 theta are the same angle. Okay, so one just rotates the detector, omega rotates the crystal. So in the case of the Kappa geometry, which is now more common, so this is the chi is made up of 2 other circles, Kappa and omega Kappa, and so here these are defined here. Here's your crystal, it's rotated. Here's chi, and so here's omega Kappa, and phi is here, and Kappa is this one. So what that effectively does is it's a more open type of geometry. This type of geometry, you have this open goniometer head, and it allows the detector and the so the detector can move around 2 theta like this, but so this is your 2 theta for the detector, but your crystal moves around in all kinds of directions so that you can get to every angle that is allowed by Bragg's law. Remember that in a single crystal we have to physically orientate the crystal with respect to the beam to satisfy Bragg's law. It's different in powders. We'll talk about powders tomorrow. And most modern instruments have some kind of image plate detector, or a charge coupled device, a CCD type detector. So essentially you have a phosphor, your X-ray photon hits that phosphor, and this phosphor gives out various photons here, and that's picked up by a fibre optic taper into your charge coupled device. And this essentially is a device for converting your X-ray photons into a digital signal. But it forms the basis of most CCD type devices today, and most diffractometers will come with a variation of this type of device, even powder diffractometers. So, unfortunately we're missing can't really see the top line very well, but I can tell you what it says. So we typically use molybdenum K-alpha radiation. So molybdenum has a shorter wavelength, about 0.7 angstroms, compared to copper, which is about 1.5. The reason for that is very simple. What we're trying to do here is, well, typically we'll be looking at organic systems, which are have larger unit cells than the common inorganic systems that are typically run on a powder diffractometer. So they'll have generally one long axis at least. So in order to see that quite well, and also to maintain the data quality down to lower despacings, molybdenum is a kind of optimum radiation. So we've got our crystal, we've got it mounted on the goniometer. We then use it's a computer controlled through the 4 angles, or some subset of the 4 angles, to give us a data set, whilst it's being irradiated by X-rays. So this is just to make sure that we make the correct Bragg angle. And then we get images like this. So this is an HOL image. So this is very similar. This is a picture of reciprocal space. So I haven't told you about reciprocal space, but if you imagine that the spacings here are proportional to the inverse of the direct space. Direct space is what you can think of in your crystal. So atom A to atom B is 1 angstrom. So in reciprocal space, that distance would be 1 over that. So 1 over 1 would be still 1. But 1 over 2 would be a half, for example. So these are the kinds of images you get. So HOL is HKO for a monoclinic crystal, and you get lots of reflections at the same time. Each of these, so if this is HOL, so this might be, I'm not sure which is H and L in this direction, but this might be 1, 0, 0, for example, and this one would be 0, 0, 1. By measuring these, measuring the intensities, measuring their positions, we get, first of all, the unit cell dimensions, and we then get the intensities of each of those reflections. And remembering yesterday that intensities are proportional to the structure factors squared, we can use that information to try and solve the crystal structure. So what we usually do is typically a set of reflections is collected in a scan of phi, so phi scan, but we can do other angles, it doesn't matter. But phi just gives us enough of a range of data usually that we can start to get the unit cell. Older diffractometers we collected 25, on new ones we do around 200 peaks. So we use a lot more data now on the new instruments because it's fast. These new instruments with the charge coupled device, the CCD, well, typically on my old diffractometer, which was a CAD4, which just had a simple detector, that would take, for a monoclinic crystal, 2 to 3 days data collection. On a new instrument with a CCD, I can collect the same data in about 8 to 10 hours. And on a very simple crystal structure, maybe about 2 to 3 hours. So much, much faster. Once we've collected those, we try and index them. I'll talk to you about indexing tomorrow probably. The index reflections are then used to calculate what we call the UB matrix. It's the matrix that tells us how the unit cell is orientated with respect to the beam. So it tells us effectively how the crystal is orientated. Now, of course, you know how it's orientated depends on how you picked it up. When you were lifting it off the microscope slide, and depends on how it froze in relation to the fibre. So that can change every time. Every time you mount another crystal, that matrix is going to change. We then set it to collect an initial set of data between certain diffraction, between certain limits of H, K and L. And then we get a new set of intense reflections that we can use for indexing. These days, that's what we used to do. These days, we basically say, go collect the whole thing and we'll worry about the orientation later. Because, in fact, the old diffractometers needed that because they drove to each individual reflection. So it would say, I have a reflection here at these 4 angles. The diffractometer would then move all its bits so the crystal was correctly orientated for those 4 angles, and it would then collect the peak. Before the peak, after the peak, the height of the peak, the background. We would do a very careful scan to get the intensity. These days, with these images that we get, you collect everything at the same time, and then you calculate, do your calculations later by image processing software. So this has speeded up the whole thing. Okay, you've collected data. You then have to go through a process known as data reduction. Firstly, you've got to correct for polarization factors. So your intensities, so these are the Lorentz and the polarization factors. And these are the Lorentz factor, the polarization factor, you can see is a function of the Bragg angle, and the Lorentz factor is a geometric factor, and it varies from diffractometer to diffractometer. So these are just corrections you need to make to the data before you can do anything. So we subtract the area of each peak from the background to give a corrected intensity. We can also apply absorption corrections. Remember that we talked about absorption yesterday. The heavier an atom is, the more it's going to absorb. There are also things like fluorescence that you may have to deal with. So we then get a set of structure factors, which when we square, we get something that's equal to the intensity. So the scaling factor is dependent on the beam intensity, so you can normalize to that, and also the crystal size. So we usually refine this scale factor as part of our analysis. The FHKL here we call FOBS, the observed structure factor. So our final results that we get from the diffractometer are, first of all, the lattice dimensions, A, B, C, alpha, beta, gamma. The indexed reflection, so HKL for each reflection. The square of that, of the intensity, FOB squared, after it's been corrected. And an error associated with that FOB squared, so sigma. And that's what you get. When you come away from the diffractometer, you have a set of several thousand reflections and the data of this form. Okay, well, you have one set of these and then thousands of these. So I mentioned about absorption. We usually do the absorption correction, and now absorption is important, as I mentioned, because also this is not like in our Bragg-Brentano geometry for the powder diffractometer. Absorption is less significant. Here we're talking about transmission through the crystal. So the size of the crystal and what's in it make a big difference. And the dimensions of the crystal as well. So we have to take all of that into account. There are a number of methods. The most rigorous method is to index the faces of the crystal and calculate the path length for each reflection. Then if you know what the contents are, then you can make the correct absorption. But lots of empirical ways, and this SADABS is virtually a standard method now. Okay, but other ways that you can look up, and I've given you some references here if you ever want to do this. So, the interesting bit, okay, most of you will never sit down and actually collect a single crystal data set, but some of you might, if you ever get the chance. It's work to do. We can divide up the crystal structure analysis into a number of different steps. The first is the cell parameter and crystal system determination. That is done on the diffractometer. You don't need to, you get that information almost straight away. We know what the cell parameters are, we know what the crystal system is. Those things are checked on the instrument. Data collection, data reduction, Again, before you ever get the data, you will have all of this done. At that point, you have to determine the space group. And yesterday we explained how you do that. You do that through systematic absences. And there are programs now that will do that automatically for you. They'll check your data and say, suggest a possible space group. But sometimes you have to do it by hand. We then obtain a starting model. That is the solution, the structure solution. We then calculate structure factors for that model and then perform a least squares refinement of the model to minimize the difference between the observed and calculated structure factors. We then calculate electron density maps to locate new atom positions and then repeat these steps, so 6 to 8, until we get a final model. And that's how single crystal structure determination is carried out. It's a very simple process, but you need to know a little bit of crystallography to do it. Not so much these days. In fact, there are programs which are more or less black box that you can come along, here's my formula, this is what I want out at the end, and hey presto, in about 10 minutes you have a crystal structure. It's when it's wrong and you don't recognize it's wrong, that's where the problem is. So what I'll try and do is show you what the programs are doing, so it isn't such a black box. And so if you ever receive a crystal structure from somewhere, you will be able to say, oh, that's not quite right. Perhaps we need to do something. So what information do we get from the structural analysis? We get the unit cell parameters. We get the crystal system and space group. So we got those original, space group is what we've determined. We get the atomic parameters for every atom in the cell. So X, Y, and Z, they're fractional coordinates. Their thermal parameters, how much they're vibrating, and their fractional occupancy. So that's important, for example, in the case of disorder. Bond lengths and angles, very important for most of us. If it's a molecular system, then you'll have a molecular structure. And then the crystal structure, as distinguished from the molecular structure, is how the molecules pack together in the crystal. So, for example, the extent of hydrogen bond is part of the crystal structure, not part of the molecular structure. So, our analysis can be divided into two main parts: structure determination and structure refinement. In powder diffraction, we focus mainly on refinement. We don't do so much determination. But the determination part also comes into it when you want to do something ab initio. As I said yesterday, ab initio from scratch, from the beginning, where you don't have any preconceived ideas about what is in the structure. So, structure determination is common to powder diffraction as well. So what I'm going to say today is good for tomorrow. So I'm not going to repeat it tomorrow. How does it work? As we said yesterday, what we get from our data collection is the intensity HKL, which is proportional to the F-ops squared. So we have the phase problem. We don't know the phase of F-ops, we only know its magnitude. In order to model the structure, we need the phase of F-ops as well as the magnitude. So our structure analysis involves phase determination. So that's what we're doing. So there are a number of ways in which we can solve the phase problem. And I'm going to talk, well, there are many more than this, but these are the main methods. And I will talk to you about each of these and explain to you how they work. So, the first one is simple. An analogy, and that's what we do in powder diffraction usually. We have something that has the rock salt structure, so we take the structure of sodium chloride, we adjust the cell dimension, change the atoms for the atom types, and put the same coordinates in. Then we do the refinement. That works very well. The second one is vector density methods, and lastly I'll talk to you about direct methods. There are other methods, some probabilistic methods, but I think we don't have time. In 4 lectures I can't do all of them, so I prefer to concentrate on the ones that are more commonly used. So structure analogy, we almost never use this for single crystal structures because you don't need to. We have so much data, we can do this ab initio. Why go along with a preconceived idea? We might as well go along with no preconceived idea and see what the data are telling us. But it's good, it's used for powders. And so we can use an example here. So here's sodium chloride and nickel oxide. Both of them have the rock salt structure in space group FM3N. Okay? We know the structure of sodium chloride, so it's got an A-axis of 5.628 angstrom. It's cubic, so they're all the axes are the same. The sodium in the 4A position, and this will be the 4B position, I think. The sodium and chlorine from this space group. So what we do is we say if this is nickel, we have the cell dimension here, it's shorter than this, but we put the nickel in this position and the oxygen in this position. And we try the refinement to see if it works. And hey presto, you have a structure solution. More useful and more commonly used are things like the Patterson methods. Okay, so the Patterson method is suitable when you have a heavy atom in your structure. So when would you use it? Organometallics or metal organics, where there's one atom in the structure and the rest of the molecule is all carbon, hydrogen, oxygen, or nitrogen. Sulfur already starts to present a problem. It's bigger. Sulfur, phosphorus, you start to get more problematic. You may have to use other methods. But this method is very good for quite a lot of structures. And it's quick and easy. So what is it? Okay. If you imagine, so the way that the Patterson method works is you produce a vector density map. That's what you're doing. And we have this formula here, so we can take our raw data, so our intensities, or our FOB squares, multiply it by the exponential of minus 2 pi I of h times u plus k times v plus l times w, where u, v and w, so h, k, l, you know, are the Miller indices. U, v and w are the coordinates inside the Patterson cell. The Patterson cell has exactly the same dimensions as the real cell, but but it's a vector map and not a map of electron density. If we multiply this by the reciprocal of volume, we get the density at a point UVW. So if you decide on if you want a map, let's say from 0 to 1, these depths are 0.1 in all dimensions, those are the values of U, V and W you put into your map. You know HKL already, you know your intensities, you know the volume. You can produce a density map very easily. Now, that density map corresponds to a pair, remember they're vectors. Vectors are between pairs of atoms. So if I have an atom here and an atom here in the structure, what we're looking at is the vector between those two atoms. And what I do is I take that vector and I shift it with respect to the origin. So it's better if I do it, let's do it this way now, otherwise it'll be difficult for me to draw the cell. Let's do that one. So if I take that vector and I have a unit cell, let's say, and I reproduce that vector in the unit cell from the origin, then I'll get a peak there in the vector map that corresponds to this vector. So the distance from the origin, so its coordinates, if you like, are the same as this distance. The height of this peak, so how intense it is, depends on the atomic number of this. So the two atomic numbers, if we multiply the two atomic numbers, we get the height of the peak. Okay, or something proportional to the height of the peak. So, if you have a system where you have, for example, you know, I don't know, a big molecule like this with some kind of organic group attached to it, let's say something like this, and you're looking at the vector between this and the next heavy atom. So the product of these two electron densities is going to be much bigger than, let's say, this vector or this vector. So the map is going to be dominated by vectors between the heavy atoms. They will appear as the maximum. So the vector between two atoms, for example here, so here's in space group P1 bar. So in P1 bar you have the equivalent positions x, y and z, and minus x, minus y, minus z. There's a centre of symmetry. P1 bar just means the only symmetry that you have is triclinic, it's the simplest type of cell. You only have this centre of symmetry. So you have these kinds of equivalent positions. So that is shifted to that distance there to give you point UVW with a height corresponding to the product of those two electron densities. So generally, for a vector between atoms point XYZ and point X1, Y1, Z1, U is going to be equal to X1 minus X, V is Y1 minus Y, W is Z1 minus Z. In this case, we can see, because this is X minus X, so the distance is going to be 2X. And the same for Y, it's going to be 2Y, 2Z. So this distance here is 2X, 2Y, 2Z. Which is good, because what we, it means that in this example, the coordinates of our heavy atom, so X is equal to U over 2, Y is equal to V over 2, and Z is equal to W over 2. And so for a very simple centrosymmetric system like this, we automatically get the heavy atom. Remember that where you have a heavy atom, it's going to dominate the scattering. So that means we already have the dominant scatterer in our model, and from that we can start to phase the data. So provided we've got a lot of scattering in that heavy atom, we can phase the rest of the data and then use other techniques to find the missing atoms. So it's a very powerful and easy way to solve destruction. Now, one thing you have to remember, the Patterson model, the Patterson cell, has the same dimensions, but it is always centrosymmetric. Because remember, you're talking about vectors between two atoms. So if you've got a vector going this way, you also have a vector going this way. So you will always have a it's always centrosymmetric. So even when the structure, the real crystal structure is non-centrosymmetric, the Patterson map is centrosymmetric. Determining the structure from the Patterson map is not always easy. It's easy when you have very simple symmetry. So back in 1935, before computers, all of this was done by hand. So David Harker suggested looking for special lines and positions. So here's an example with a monoclinic crystal with PM symmetry. Now, what is PM symmetry? So PM symmetry is just, it's got a mirror plane. So if this is our unit cell, so if I have an atom here, it's got a mirror plane. If this is the B axis over here, it's got a mirror plane, and then I have another atom here. So very simple symmetry. So in the real cell, this would be X, Y, Z. In the and its equivalent position would be X minus Y, Z. So it's just a reflection perpendicular to the B axis. So in our Patterson cell, we should be looking for special types of lines. Okay? So there will be a lot. So imagine there's lots of atoms that have this symmetry, and they're all producing this type of vector. So we will have lots of vectors where you have X minus X, Y minus Y, and Z minus Z. So it means we're going to have lots of them where we've got 0, 2Y, 0. If you see a lot of those, you know you have a mirror plane. And so it's relatively easy then to work out where your atom is going to be. Yesterday we talked about the two screw axes. In this case, you've got atoms related by this. So X, Y, Z, and X, Y plus a half minus, sorry, minus X, Y plus a half minus Z. So you're going to see lots of peaks at the time. 2X, a half, 2Z. When you see that, you know you've got a two screw axis. You look for these certain types of vectors in your map, and you can already start to determine the space group and start to get information out on the structure. So this would give you, you get the X position, you get the Z position, and then you have to look for the Y. So because the height is proportional to the product of the atomic numbers, the vector map is going to be dominated by these heavy atoms. And so it's suitable for that type of structure. Once we've got the heavy atom, we can do the initial phasing of the reflections and then use difference maps to find the remaining atoms. This is now almost fully automatic in programs like ShellXS. ShellX, by the way, is probably the standard for doing structure determination. So ShellX, ShellXS and ShellXL, they're free, available for everybody to use, and they are, so S is for the solution, L is for the refinement. So So those two pieces of software are now the crystallographic standard across the world. So if you ever need to do any, and even for powder diffraction you can use it, if you're using pseudo-single crystal data. Now, the next method is direct methods, and this is horribly complicated, so I'm not going to go into a lot of the theory, but I'll just try to give you a little bit more insight than most people have. Because, you know, years ago when I was teaching this to students, I would not spend a lot of time on direct methods, but it's used so commonly. So this is used when you have structures where there's no single heavy atom, or where you have lots of heavy atoms and you can't distinguish it. So it's used where you can't use any other method. So very common in pure organic systems we would use this, or in systems where you have like, a lot of inorganic systems where we don't have where we have not just a single heavy atom type. It's complex, and I'm not going to spend a lot of time on it, but I'll tell you a little bit about how it works. The first stage is the normalization of the structure factors. Remember that the structure factor and the magnitude of the structure factor vary with the Bragg angle. So in order to compare your observed structure factors, we're going independent of the angle, we need to normalize. And so we use this normalization factor here. So your structure factors are just normalized over the sum of the scattering factor multiplied by this Debye-Waller factor, which is essentially telling you about the vibration. We then assign tentative phases to these normalized structure factors using the magnitude of the structure factor. Now, how do you do that? So we're saying that the big structure, you know, the big structure factors, the ones that have a lot of magnitude, how do we determine a phase for them? Well, let me show you now. You basically have a set of phase relationships set between the most intense reflections. Let's show how this is done. If you want to look at this in more detail, this is available online. You just put in for a Google search for this and you can download this. It gives it in much more detail. But this is one of the diagrams. So, why are larger FOBs more important? So we get larger FOBs when the atoms, lots of atoms lie close to the plane. Remember that we have an infinite number of lattice planes, okay, in our crystal structure. If we have atoms which are close to the plane, like in this example, you have a larger scattering than in this case where the atoms are further away. So here we have a smaller FOBs, here we have a larger FOBs. So the larger ones are telling us that the atoms are close to these planes. We already know the positions of those planes. So we already have some idea about the positions then of the atoms in the structure. So these ones are more important than these ones, for obvious reasons. You then try and set up some phase relationships. And there are lots of different ones, but I'll only talk to you about one of the simplest ones. But, and let's just consider it. This is the epsilon 1 phase relationship. And it looks at the relationship of something like a structure factor with 2H, 2K, 2L. Okay? So it tries to estimate, if we've got, for example, 1, 1, 1, it will try to estimate, so F111 or E111, it will try to estimate E222 from E111. So looking at the relationships between these two reflections. So, in centrosymmetric structures, only phases of 0 and pi are possible. Okay, so we actually looked at that a little bit with when we were looking at systematic absences, you could see that it depends on the intersection of the constructive interference. So you'll only get two possible phases: in phase, or at 0, or at pi. So looking at these two reflections, 110 and 220. If the phase of E110 is 0, then the maximum in electron density is found on those planes. Okay? And the minima are halfway between them, because we know that the phase is going to be only 0 or pi. So if the phase of 220 is 0, then its maximum will lie at points 1 and 2. So here's your cell, here's your 110s, these big ones here. Okay, so that's 1, 1, 0. Here's your 220s, which lie in between. So if we know the phase of 110, okay, if we assume the phase of 110 is going to be one of these, and then we should know the phase of 220. So the phase relationships are all about this kind of thing. If we know one, we should know the next one. It's about those relationships and setting those up. And if you do that over thousands of reflections, you start to have an idea of what the phases should look like. Because they all have to obey certain rules like this. So we can apply similar methods for other phase relationships, and that's how direct methods work. They set up these phase relationships. We then use space group symmetry to determine which of the phase relationships are important, because you have allowed reflections and disallowed reflections. That we call convergence, and you use these relationships as a starting point for phase determination. And you determine those. There's a horribly complicated multiple tangent algorithm that you use. I'm not going to show you that. You use that for your initial phasing of the data. So you have some initial phase, you have these phase relationships, you then try to phase them using this multiple tangent algorithm. From the phase data, we can generate electron density maps and locate atoms in the crystal structure. That's how direct method works. And it's very, very powerful. It will work not just for it will work in the majority of cases, provided your data quality is good. Of course, you don't have to understand all of this, but it's quite useful for you to understand what's going on in the black box in shell XS when you press, oh, I'll do direct methods, I press that button. What's going on? That's what's happening. Now, we've talked about electron density maps. You can generate this through a Fourier summation. This is very similar to the equation we saw for the Patterson density map, okay, except now we're not using the square, but we're using f odds directly. Okay, and we're multiplying by some phase. Okay, and this is the phase that we've just calculated, using either by direct methods or by Patterson methods. And we get the electron density at every point, and using that, we can start to look for atoms. More usefully, what we often have in a crystal structure analysis is we have one or two atoms, and we want to find the rest. How do we do that? Well, instead of having this part, we just change that. We subtract the calculated structure factors from the observed structure factors, and we get the difference Fourier map. That's probably the most important map you use in structure determination, because this is where, for example, you've got part of your molecule, I want to find how it links together, that's what you use. Use a difference Fourier map, and you can set this up so you can search this map automatically. How do we tell how good it is? Well, we have things called R factors or residuals. Remember that this is a least squares procedure. So least squares works with a residual sum of squares. Okay, so it's looking at the difference between the observed and calculated. And there are various ones that are used as standards. So this weighted residual here is commonly used, or R1, which is a very simple one. F odds minus F count, just the magnitudes, divided by the sum of F odds. So that's very common. This is also common. And this is more like chi-squared. The programs work by trying to minimize usually R1 or WR2. Okay, so it's doing its refinement trying to minimize that difference. Oh, you can't see this very well, but this is basically a spreadsheet, a flow chart telling you the different stages. Okay, I won't waste time on it. You can, if you want to if it's available, you can have a look. This was actually many years ago. I did this for my PhD thesis. It summarises the basic methods and the loops you have to go through. So some parameters that you need to know of. The thermal parameter we've mentioned. So these are the things that you'll see in papers. The thermal parameter depends not only on its atomic, scattering is dependent not only on the atomic number, but also on how much it vibrates. Remember yesterday I told you, if an atom vibrates, its electron cloud looks bigger to the X-ray. And that means that there's more destructive interference and the scattering falls off as you increase the angle. So it's quite important. At room temperatures and above, there is significant thermal vibration. Down at liquid helium temperatures, we get virtually no vibration. If the vibration is considered to be the same in every direction, then we call that isotropic thermal vibration, and it's a single parameter that defines that. So it's B, this parameter here, where we multiply our structure factor by this factor here. So B is your isotropic thermal parameter, and it's given in units of, I don't think I've said it, units of angstrom squared. Okay, so B values typically are around circa 1.0 angstrom squared for a typical atom at room temperature for B. A lot of the structures that you see, so in the older crystallographic programs, the B value, you'd see B values. These days you see something called U, so U iso, and it's 8 pi squared times U equals B, and these are typically around about 0.02 angstrom squared. So that would be a U value. Make sure you know which one you're using in the paper. Okay, one will be called U, one will be called B. Both get deposited in the databases and both get reported in papers. It's just to know the relationship between the two. In a typical single crystal structure, you wouldn't assume atoms are not like this. Okay, so for example, if you have a methyl group attached to some sort of, well, let's say to a ring, to an aromatic ring, this methyl group is going to vibrate much more in this direction than it is in this direction. So there's much more vibration this way. So it's not isotropic. And so what we then use are, we use an anisotropic vibration. We then have 6 parameters, which you see defined as this: U11, U22, U33, U12, U13, U23. So they're just they tell you about the directions. Okay, 1-1 is the pure A direction, 2-2 is the pure B direction, 3-3 is C, and 1-2 is the interaxial direction. 6 parameters now, and so we're in an isotropic system. You get a nice sphere to describe your atom. In an anisotropic system, you get this thermal ellipsoid, as we call it. It's often drawn like this. Okay, so this is football, and this one is rugby. That's the easy way to remember it. So they're describing the same thing, how much the atom vibrates, what they're doing it. This is a much more realistic description, but you have to have more data to do it, which is why you can do it in single crystal, not powders, very easily. And finally, last slide. The last thing you need to know is, how do we calculate bond lengths and angles? Sometimes in the paper they won't give you all the angles that you want, or you want to calculate angles over a greater distance. So this is the general thing for a triclinic cell. So this is this will work for every crystal structure. Okay, these go to 0. Okay, when your angles are 90, so you don't need to worry about these. Okay, but so essentially, it's the difference between the A, B and C directions of the X, Y, and Z coordinates. Okay, squared. That's your distance, and the angle between atoms A, B separated by distances. So if you first need to calculate your distance, and then just use essentially triangle rules to work out your angles. That's how most programs work. There are methods to calculate the estimated standard deviations, but I won't tell you about those. They also involve, remember that your standard deviations, this is a refinement. Your standard deviation involves the covariance matrix. So it's not just a simple standard deviation. You must include the covariance of 2 parameters in order to get the correct standard deviation. So ShellX does it properly. Some other programs don't do that properly, so you have to be a bit careful. So, 6 o'clock, it's time to finish, I think. Thank you very much for listening.
Any question?
No. Okay, I'll make the talks available because there's information there that you may want to use. So if
you'll file the money, so I can distribute it.
So you can have your own copies.
Thank you, so see you again tomorrow evening.